Hi, welcome to 6.6 day one for Algebra 2. Today we're going to work on solving some exponential equations. So one important property we need to recognize is the property of equality for exponential equations. So for example, let's say I have something like this. B to the power of x and I have equals b to the power of y. Well, the definition says x has to equal y because b equals b, which should make sense naturally. For example, if I have 2 to the squared power and I have 2 to the power of x, well, these 2's are the same, which means the exponents have to be equal, which means, therefore, x has to equal 2. So let's use it to solve. Next one. We have 7 to the power of 3x plus 5 and 7 to the power of 1 minus x. I have the exact same base numbers, which means the exponents have to be equal. So 3x plus 5 has to equal 1 minus x. From there, I can just solve traditionally. Get all my x's together, so plus x, 4x plus 5 equals 1. Get everything away from the x, so minus 5. You get 4x equals negative 4. Divide by 4. We get x equals negative 1. Technically speaking, I can plug it back in and check. So what's 3 times negative 1? Well, that would be negative 3 plus 5 gives me 2. So this whole thing on this left-hand side has an exponent of 2. Well, what's 1 minus negative 1? Well, that would be 2 as well. Over here on number 7. Well, my base numbers aren't the same. However, 25 can be written as 5 squared. So I'm going to replace the 25 with 5 squared. So my left-hand side stayed the same. And I'm going to get 5 squared. And I still have this x minus 5 up there. Now, I treat this as it's separated by a parenthesis, which means these exponents get multiplied. So I'm going to have to distribute this 2 right here. So I get 5 to the power of x minus 3 equals 5 to the power of 2x minus 10. But now I have the same bases, so my exponents have to be equal. So x minus 3 equals 2x minus 10. Get my x's together. Negative 3 equals x minus 10. Get everything away from the x. So we get x equals 7. Okay. Now, this process works when I can easily get the same base number. 25 wasn't the same, but I could get it to a 5 just fine. That's not always going to be the case, though. So let's take a look at problems like that. For example, 2 to the power of x equals 5. Now, the nice thing is we can rewrite it in logarithmic form based on what we've done in the past. So, quick reminder, whenever I have an exponential form, that is the same as logarithmic, just reworded. So, if you remember, when we converted to logarithmic or vice versa earlier in the chapter, we did the spiral. So I'm going to spiral this. So I get log base 2 of 5 equals x. Well, the nice thing is, log base 2 of 5, I could type that directly into my calculator. So math A log base 2 of 5 gives me 2.322 equals x. Here, same idea. I would get log base 7 of 15 equals 9x. My x isn't by itself, so I would divide by 9 at the end. But I could type this whole thing in my calculator because that's all just numbers. So, math A, log base 7 of 15 divided by 9. We get 0.155. Okay, we're here. I see that I have the exponent up here. Now, I actually have to do a couple more steps here. You have to isolate whatever has the exponent first. So over here, the 2 to the power of x is already by itself. The 7 to the power of 9x is already by itself. So I would actually have to add 7, 4e to the negative 0.3x equals 20, and divide by 4 first. So I get e to the negative 0.3x equals 5. You have to get whatever has the exponent by itself first, then you can spiral it. So I could spiral this. And then I got to remember that e goes with the natural log. Those go together. So this would actually be natural log of 5 equals negative 0.3x, which means then I could also divide by negative 0.3x to get x by itself. So we get natural log of 5. Make sure we close the parentheses. Divide by negative 0.3. And we get negative 5.365. All right, let's try a story problem. So, popular formula that comes up would be here Newton's law of cooling. You can see that T, the big T here at the end, is kind of like the final temperature. T sub 0 is your initial temperature, because 0 being when time is 0. T sub R is your room temperature. R is your cooling rate, and little t is time in minutes there. So you are cooking leche, an Ethiopian stool. When you take it off the stove, its temperature is 212. So that would be my final temperature. The room temperature is 70, so that's going to be my T sub R. And the cooling rate of the stew is right there, that's my R. How long will it take to cool the stew to a temperature of 100? Oh, I'm sorry, this would be my initial temperature because that's how much it's going to be. And this is be my final temperature at the end it's asking about. So the only thing I'm trying to figure out is how long. I'm trying to find little t. So let's plug everything else in. So we get 100 equals 212 minus 70 e to the negative 0.046 t plus 70. Let's simplify what we can. Well, these are being subtracted. I can just do that. So I can do 212 minus 70. I get 142. I can subtract the 70 from both sides. So I'm going to get 30. And remember, I'm trying to isolate this. So next we would divide by 142. We get that right there. Does that have a nice fraction? 15 over 71. You don't have to do it as a fraction, but I just find it more consistent. Okay. And then from here, I can spiral it. Again, I'm spiraling with an E, so I'm going to do natural log. And then I'm trying to get t by itself, so I'm going to divide by this coefficient here. So we get natural log of 15 over 71 divided by negative 0.046. And I would get it take roughly about 34 minutes. Thank you for listening, and I hope you have a great day.